Hi, good morning, everybody. Let me know if people can't hear me in the back. Anyway, so I'm Ratul Mahajan, and I'm going to talk about some work we've just started doing with my advisors, David and Tom, at the University of Washington. And it's about managing interdomain routing in a very cooperative manner. So here's the problem we are trying to tackle, that mainly interdomain routing or BGP policies, interdomain routing decisions, they are based on very little information about other networks. So what I do as an operator while trying to manage my own network is take decisions that are based on the state of my network without knowing what's happening in the other networks. And some of the bad effects Randy talked about at a global scale, what happened when in this situation. In particular, you can identify three undesirable consequences of this state of the world. One is poor performance, that bad paths are chosen even when there are better paths present in the network. The other being instability and oscillations, something when BGP does not converge, or because local decisions are being made without any global view, we get into some sort of oscillatory behavior. I'll get to the examples of these two in the next couple of slides. But there's an even bigger cost, which is the cost of managing these networks is high. Just because we are taking local decisions without any sort of global view, operators have to be manually involved at all times whenever making interdomain routing policy changes or rerouting their traffic towards some other direction. So here's a simple example of poor performance. Just consider a simple case of two ISPs. Those three links in the middle are basically peering links between those two ISPs. And I'm going to talk about just two flows. One of the flows going from ISP A in that dot to ISP B, and the flow back. So what happens when ISP A wants to send traffic to ISP B, it picks what it calls the earliest exit. Since ISP A does not know where the traffic is headed inside ISP B, the best it can do is to optimize the cost of carrying traffic within its own network, and hence picks the early exit, or basically what we call hot potato routing. Purely in terms of the path length, this path would have been better, but ISP A cannot do that because it doesn't know where the traffic is headed to within ISP B. And also the fact that this path is much cheaper for ISP A, so it's taking a locally optimal decision. But if you think about what happens on the reverse flow, ISP B takes a similar decision of early exit, and we end up with both ISPs taking early exit, and the net cost now for both ISPs, not just for ISP A, is much higher compared to this particular, what you might call an optimal from a path length perspective system, that both ISPs using the middle peering link and doing that. So the good thing about this solution is it's cheaper for both ISPs, and also end-to-end path length is shorter. And the point is currently there's no mechanism in BGP to let you do that. You could use MEDS, but MEDS basically means that instead of the upstream ISP chooses how the traffic goes, the downstream ISP chooses what to go. So in this case, so if both ISPs were using MEDS, we just get the reverse of hot potato routing, where the traffic flows in reverse with no reduction in path length whatsoever. So that was an example of poor performance, and also said it can lead to instability or oscillations in certain cases. So here's an interesting example of that. Again, consider two ISPs with three peering links between each other. And we're going to talk about two flows going in that direction, the orange flow and the blue flow. And assume that what happens when the peering link between the two ISP fails. Now ISP A is forced to read out this traffic. So what it does, it looks at the state of its own network and say, okay, I'm going to choose the bottom peering link for both of those flows. So what happens as a result, of which ISP A is actually not aware of, this causes an overload inside ISP B. And what B does, an operator on the B side comes along, oh, one of the links inside my network is overloaded, let me shift some traffic from the bottom peering link to the top peering link, using some BGP mechanism, either prepending or local prefs. So it does that. But what this does, now ISP B has taken a locally optimal decision in moving the traffic upwards, but this causes an overload inside ISP A. So what A does, A comes along and moves the traffic right back, or something similar that goes to the same path. Well, B notices this change, moves it right back. And I'm not making any of this up. This was actually an incident that happened between two big ISPs, I was told, and this went on for 2 days. Operators on both sides were changing their routing configuration every 30 minutes or so. And at the end of 2 days, they realized that what was actually going on, that both operators were undoing each other's work. And if they were actually talking to each other, you could imagine there are solutions in the system that do exist where no oscillations happen, and you can come to routing both flows in a manner which is acceptable to both ISPs here. So what is the current methodology when it comes to making interdomain routing changes? So whenever ISPs want to make any sort of interdomain routing changes, either in response to addition of peering links, failures, or changes in traffic due to DOS attacks or flash crowds, the first is what we call tweak and pray. So you want to make some routing decision and you just change it. And then you pray that things would be okay and you haven't adversely impacted anybody. Now this, I guess, works only for those of us who are religious. And for the rest of us, it just fails. So what you can do next is you can do something better. The problem with tweak and pray is you might not observe the problem in your own network, but there might be a problem in somebody else's network, and that other operator is now racing against time and fighting to understand what went on. So to remedy that, what you can do is call ahead. If you wanted to make some change in your own network, and if you know it would adversely impact some particular neighbor, you call them, okay, I'm going to make changes at 12 o'clock tonight. So this way at least, even if it causes problems inside their networks, they know what the cause of the problem is and they'll give you a call. So what you do is you call ahead, make changes, and hope that you don't get a call from your neighboring ISP. Because if you do, you make another change and start hoping again. So a better way out of this dilemma of making changes basically based on just local information is to basically call the operator and manually negotiate a set of mutually agreeable solution. You talk to the other guy on the phone and say, okay, this is the situation, these are the set of flows I want to read out, or these are the changes I want to make, is this okay with you? And the cost of this solution, while it works and it's probably better than the other two options, the cost of this solution is just the human coordination time, which makes it very expensive and is probably not practiced often unless the change is really major. So here's the challenge for us. Can we automate this inter-ISP negotiation? Can we, instead of letting operators negotiate manually on the phone when it comes to, can we automate it? The benefit, of course, is that you can now negotiate even for minor changes without any human cost involved. For automatic negotiation to be successful, it has to achieve these three criteria. First of all, it has to minimize manual firefighting, because that is our primary motivation behind it. If we can do that, then operators, you can imagine, they would start using automatic negotiation, and we would rely less on operators firefighting whenever routing changes have to be made. The second thing is the solution that automated negotiation should produce, they should be as good or maybe even better than manual negotiation, because if they are not, you can still imagine expecting operators to tweak their traffic even after automated negotiation has been done, and which basically undoes all the work we are trying to do here with automatic stuff. The third and the most important thing is whatever negotiation protocol or framework we design has to honor certain real-world constraints of the world we lived in. And we've identified three such constraints: that there should be controlled information disclosure across the ISPs. We live in a world where ISPs are competing entities, and there are competitive concerns due to which ISPs would be reluctant to give away all the information about the internal state of the network to other ISPs. So we do not want a negotiation protocol in which one ISP has to tell the other everything about the state of its network and minimize this information that flows across the ISP boundary. The second constraint is that the negotiation protocol should be independent of the optimization criteria itself. It should not be focused just on optimizing latency or just on optimizing resource utilization in a network. And the primary reason there is twofold. One, maybe ISPs don't want to reveal their optimization criteria. And the second reason is that, which is more important in some sense, that different ISPs you could expect are optimizing their network for different things. One might be optimizing for latency, and the other one is just optimizing resource utilization increase inside its own network or protecting certain links that tend to overload. So the negotiation protocol has to be such that these ISPs with different optimization criteria can still negotiate with each other to find mutually acceptable routes. And the third is flexible outcomes. Different pairs of ISPs have different relationships with each other. Some might be peers with each other. Other ISPs might be providers or customers. And you could imagine when these two ISPs negotiate with each other, they would want different solutions. So what we are not looking for is a mechanism that, given some input, produces a fixed output, but we are looking for something that's more like a negotiation, where the outcome of the negotiation actually depends on the people who are involved and the relationship between the parties that are involved in there. So here's the current status of our work. We've just looked at negotiation between two neighboring ISPs as of now. I mean, you could imagine this negotiation happening at an internet scale, where all the ISPs negotiate all the traffic across whichever paths, whichever ISPs the traffic is using, all of them know traffic is flowing through them where, and you could imagine a global negotiation. But so far what we've looked at is a simpler but still challenging problem of just negotiating between two ISPs. It basically boils down to picking a peering link between them when there are multiple links between them. And what we've come up with is a fairly high-level methodology. So I have to warn you, I'm not going to talk about protocol details because we haven't really focused on details yet. But we just wanted to come up with the high-level methodology, how this should work, and evaluate the potential benefit of it. And if it turns out this is actually beneficial, we might just go down and come out with a very detailed proposal on this issue. So here's a simplified view of the negotiation methodology we're talking about. So suppose two ISPs are negotiating with each other, and they have a bunch of flows to route or reroute between each other. So for starters, we say, well, let them assign a numeric preference, just like MED, an opaque number. Let them assign a numeric preference to each of the option for each flow. So between two ISPs, an option is basically which peering link to pick for a particular flow. So good thing about using this methodology is that first, this number is completely opaque. I hand you a number 20 as an ISP, and you have no idea what I'm talking about. How did I come up with that number? So my optimization criteria is hidden, and you don't know what, like 20, even the magnitude or what I'm using basically is not clear to you. So very little information is revealed, and no more than what's revealed using MEDs today. Second, so both ISPs have come up with the numeric preference, and the second, they exchange these preference lists. And the third step is the most flexible part of the component here, that ISPs take turns to propose options. And while proposing options, as in a peering link for a flow or something, they find good compromises in the preference list data. And I'll come to an example on the next slide. And in the middle of the negotiation, you might want to reassign the preferences. After some of the flows have been negotiated, the load in the network changes, or the potential load in the network changes. So you might think about reassigning the prefs and redoing the negotiation step. And it's flexible and stop whenever one of the ISP wants to. One of them can, okay, I'm done, I don't want to negotiate anymore. And that's when the negotiation would stop, and you would then go ahead and implement whatever you want, whatever you negotiated in your network. So here's an example. I'm going to talk about the simpler of the two examples I talked about, where they were trying to reduce the latency of the paths between them. Again, two ISPs, A and B, and two flows, the blue flow going from A to B, and orange one going from B to A. The matrix on your right is basically the preference list. So over here I'm saying, so 0 is basic. I put the numeric preference for the default routing paths, shown here in dots, in zeros, just to evaluate how much benefit they get otherwise. So for A to B was using the bottom peering link, so the preference for both ISPs here is zeros, and B to A was using the top peering link, and the preference is 0. And now for the A to B flow, the first entry in each of these pairs is the preference for ISP A, and the second column in all of these is the preference for ISP B. So let me just work through this one. For A to B flow, what ISP A is saying, it's slightly worse for me to take the traffic to the middle peering link. So it assigns a -1. But taking it to the top peering link is even worse for me. So assign a heavier negative preference, -6. Similarly, B saying for A to B traffic, it's best for me if you bring it from the top link, that's 6. And it's still good for me if you bring it here, and this is just the default. So let's say ISP A gets to propose an option first. So what it does, it looks at its preference list. Okay, this is the default anyway. Can I do any better than what I'm doing now? It looks here 0, -1, -6. No. So this is my best option. The default I'm good with. But then it looks in this case, oh, there's some place for optimizing flows going from B to A. So it looks so this is 0, 0 default. But looks here, it's 6 and -6. You would think that ISP A is tempting at proposing this option, but it knows if it does that, ISP B is unlikely to accept this option. So instead of proposing this, which is highly negative for ISP B, it tries to find a good compromise here, which is much better for A, but only slightly worse for B. So what it does is proposes this option. And you could imagine, since this is just slightly worse for ISP B basically accepting that. So B does the same calculation and proposes this. So what we get is this solution. And if you add up preferences as some rough measure of how much the ISPs have gained during the course of the negotiation, you can just add, you can add, okay, this -4 and 4 here, so it's gained 3, and similarly for ISPB has gained 3, and end-to-end paths are even better. So this is basically the insight behind why negotiation would work, that both ISPs are actually trading small sacrifices whenever the flow is routed not on the default path for bigger gains. And if you put together such options or such trades, what you get is better performance for both ISPs individually and for the end-to-end path over there. So we evaluated the potential of this negotiation using, we had measured data for POP level ISP topologies, and this data set basically contains measured topologies of all tier 1 ISPs and a large number of tier 2 ISPs. And we play with all sorts of synthetic traffic models to understand, since we don't have data available for traffic, like what's the nature of the traffic that flows across these backbones, we came up with several synthetic traffic models and evaluated our results for each of them just to see if our results are sensitive to traffic models as such. And what we did basically, we compared 3 routing methodologies. One is just the default, early exit, selfish routing. Each ISP is looking at its own network and routing traffic using that. Optimal. And optimal was basically what is the globally best solution across both ISPs. And the definition of optimal is dependent on the metric we are trying to evaluate negotiated routing on. So I'll come to that in a minute when I talk about specific experiments. But the difference between optimal and default, it just basically gives us some sense of how much opportunity is there to negotiate. If the difference between optimal and default, what happens today, is not much, then there's no point to negotiating because we are living in a very efficient world as is. And the third solution, third routing methodology we evaluated was just negotiated routing and what happens with it. I'm going to talk about 2 sets of experiments, one for latency reduction, how much negotiation helps with latency reduction, and the other is hotspot avoidance, what happens with short-term overloads in one of the networks. So here's the experiment for latency reduction, and the insight behind there, or the motivation is just that high latency basically implies poorer performance for your customers and through the network. But it's not just that. High latency also impacts the ISP network itself. If there are shorter paths present in the network but longer paths are being taken, that basically means more resources are being consumed within the network, which in turn could translate to a costlier operation. So with this motivation to evaluate the reduction in latency using negotiated routing, what we did was measure latency of traffic when routed using the 3 routing mechanisms I talked about, default, optimal, and negotiated. And optimal in just sense basically means, since we know the latency of traffic in both ISPs, optimal basically is what is the best across 2 ISPs, not caring about how much an individual ISP gains or loses in the process. So here's some results. What this graph here is plotting is total reduction in latency across both ISPs and reduction compared to default. The solid line here is for optimal traffic. What reduction using the optimal routing strategy, what is the minimum across both ISPs, and the dotted line here is for negotiated traffic. And what this graph here, for this point here, for instance, is saying that for 60% of the ISPs, the reduction in latency is 5% or more. And there are 2 things here. One is the negotiation is very close to optimal. So what this is saying is by negotiation you can come very close to optimal by itself. So there's not much cost to just negotiating instead of finding the true globally optimal. But there's another thing going on, that there's a very small aggregate latency reduction here. There's like 5%. Or the median's even less. But when you dig deeper, there is some flows that really gain big. And these, I suspect, are the flows which really suffer using early exit routing because traffic is routed in the opposite direction altogether. And at this point, it's not clear to me whether this small aggregate reduction is actually valuable in terms of the benefits it brings. But this is something I'd like to get your feedback on, or whether it translates into any sort of monetary advantage or not. But there's a more interesting thing happening here. I mean, we saw that optimal can be computed, at least for latency. The interesting thing here is what the graph on the right is plotting. What is the reduction in latency inside each individual network as against across both of them? So what we see is if you just try and achieve the optimal, one of the ISPs actually suffers a negative reduction. It basically means by moving from default to the optimal scenario, it just so happens that one of the ISPs or latency inside one of the ISPs actually increases. Which basically means that this ISP maybe will have no incentive to negotiate because its latency is increasing as a result. But the dotted line here for negotiation basically shows that ISPs either don't win or both win. It's basically a win-win situation that you have nothing to lose by negotiating. You're bound to not lose at all. You might just win. Let me talk about a more interesting experiment now, which talks about dealing with short-term overloads. So sudden changes inside even a well-engineered network can cause short-term overloads, and these sudden changes could result from failures, DOS attacks. Maybe addition of link is not a sudden change, but it still leads to rerouting of traffic, and that can cause overload in certain links. And fighting these, I understand, is a major time sink for operators today. So we tried to evaluate whether negotiation can help with hotspot avoidance or not. This experiment is 3 steps. Assume that a peering link between between two ISPs fails. And what we do is reroute the traffic traversing the failed link. And this rerouting happens using those 3 routing methodologies I talked about. The default, selfish routing. The second is optimal. And optimal here was computed using this complex constraint solver that was sensitive to load on the individual links. And negotiated routing. And negotiation, the metric used by both ISPs in negotiation was, again, since we're evaluating for load, was basically overload in the network. And the third is we measure the potential with each of these methodologies, and the metric for measuring hotspot potential is the increase in the link load before and after the failure. And the thing is, the intuition there is if a link carries 10 times as much traffic after the failure as before, then the chances are that link is loaded, would be loaded after those changes, after rerouting. So here the experiment. These graphs are a little different from the ones I showed, so I'll just walk through them. This is, again, experiment for all the ISP pairs. The graph on the left depicts what happens inside the upstream ISP, and this graph depicts what happens in the downstream ISP. And the x-axis is basically the multiplicative increase in load relative to the optimal. So there is some optimal strategy which basically focuses on reducing overload inside both ISPs. And what do we do when we, and compared to that optimal, how do negotiated and default routing do? So what we see here, and the dotted line is again for default, and the solid line is for negotiated. So what this point here is saying is that load ratio was like twice the ratio, basically means a 200% increase in link load compared to the optimal over here. So what we're seeing here, just by the shape of the curve here, is that there are certain links. If you use default routing, there are certain links in the topology that would carry 200% or more load. So the tendency for the links to get overloaded is much higher with default routing. And ideally what you would want in any solution that to come close as to the optimal is something like the negotiation, a line that goes all the way up to 1. So negotiation we see, since it's like, it does go all the way up to 1, but it closes there. So in sense it's very close to the optimal, but not quite. There's some cost to that. But nevertheless, you can see that negotiation reduces the possibilities of hotspots in the network. Once the possibility of hotspot reduces, then this basically means there are fewer problems for operators to resolve because no short-term overload happens as a result of changes in the network. So I'm going to conclude my talk here and basically just summarize what I just told you, that the motivation behind our work basically here was interdomain routing or BGP policies are based largely on local information, and which has cost in terms of the quality of the paths we can achieve, the poor performance of the paths in steady state, instability in the face of changes that come by in the network, can lead to oscillatory behavior with people making changes independently without any sort of global view. But a bigger cost is in terms of operators' time. The management is tedious, it's error prone because of humans are involved in the loop. And what we started investigating was, can all of this go away in terms of management cost and the performance cost by just automating the negotiation? And our early results basically point that automated negotiation can help, and none of the ISPs actually loses by negotiating, and which is the way the whole negotiation framework is set up, that you are guaranteed to not lose during negotiation. And I'd love your feedback on it, and basically just one question in terms of, from whatever sense you've gotten out of it, would you use it to talk to your neighbors in the sense, in what scenarios automated negotiation makes sense, in what scenarios it does not, what kinds of problems it solves, why it's not possible to do that in the network. While I focused on latency reduction and hotspot avoidance, you can think of automated negotiation as a load balancing tool that you use with your providers or customers when you're trying to balance load across multiple providers or across peering links of the same provider answer. And there's a paper available on that URL there that talks about the experiments in detail, which I didn't get time to, and explains the whole thing in more detail than I could get to in my talk. Thanks.
Nick? There you are. Yes, there's time for questions here, please. We just didn't see anybody leap right up. So stay here for a moment, please.
Okay.
Because I think this was a very interesting next step in how to do that. So if there's questions, please rush right up to the mic right now, because we're a little tight on time. So.
Yeah. I'm Manish from Merit Network. I had a question regarding your approach in addressing this problem. Now, a lot of words that you've used seem to be indicative of using the min-max principle in game theory and global optima. So is that the approach that you're taking in this work?
We are still looking at this, so we are still looking at game theory, but from a different perspective. We're looking at game theory mainly. What can we say about the incentive compatibility and things like that of the solution? And I mean, and just articulating the properties of the solution in terms of Pareto optimality or just social optimal, and things like what the impact would be of the resulting solution when one of the ISPs begins to cheat and things like that. We haven't made much headway in terms of actually applying some solid tools from game theory and infer certain nice properties that you might want out of it. But if you have ideas, I'm happy to talk to you after that.
Thanks.
But you're right, in general, game theory does look like a tool that it's meant for scenarios like this.
Bruce Hanna from Park. It's a little hard to tell from just the cursory overview presentation here. It seems like the assumption you're making is where you've got provider A and provider B, that if they both play nice and decide to cooperate with each other with this automated protocol, then there's mutual benefit. The previous questioner brought up the issue of game theory. It seems to me you can end up in a prisoner's dilemma situation where I, as the bad provider, try to trick the other guy into being nice to me, but in the meantime I'm backstabbing him by taking the low-cost route, right? So I try to make him take a path that minimizes my cost, but in the meantime I'm taking my low-cost egress and making him pay to carry the traffic. So does your research address the situation where one provider tries to defect from the cooperative arrangement and trick the other guy into cooperating?
It does so, but in a very trivial manner. And the trivial manner is the following. If you know the default routing, then no matter what the other ISP says, the other bad provider says, you cannot lose by negotiating. So now the point becomes that you have in this default scenario in which both ISPs realize what the cost is. And as a provider, I know what my cost is, and by negotiating with you what my cost is, what the cost of the negotiated solution is. So the trivial answer I was pointing is basically that I will not negotiate if I lose. Now, it's in the cheating ISP's interest to actually give me incentive to negotiate. And, because you gain a lot, by cheating you gain a lot by negotiating, but you also have to basically give me some carrot to play, otherwise I'm not going to play at all. And so then the issue becomes that yes, there is some margin for cheating, and the result of that cheating is that the gains from negotiation may or may not be divided in a fair manner, whatever the definition of fair might be. And we are still looking into this whole fairness issue, but beyond that we don't have a good answer yet.
Okay, so I'm guaranteed not to lose, but
yes,
my competitor might gain more than me.
Right, that's true.
Okay.
Yeah, thanks.
2 questions, that's it. Yeah. Randy, that included you, if you wanted to ask.
Okay, this is on. Right. Tom Vest, no fix addressed. Actually, I wanted to address the game theory issue as well. You start off with mentioning that this assumes absence of local information, but in fact the model you set up, which is correctly identified as a prisoner's dilemma, in a way implicitly assumes perfect information on both sides. The way you've set it up is the incentives are equivalent or symmetrical. In most real-life circumstances, and consider even peering between two peers, generally they won't perceive each other as absolutely identical. And since most of the interconnections are actually not peering, but are some sort of compensation-based arrangement, you'll almost never get a situation where the two parties actually do, in reality, without knowing it, have perfectly symmetrical views of the relative merits of coming to an agreement. So you always have somebody who sees the relative gains issue. In fact, this is sort of the shipwreck of game theory outside of this sort of network modeling world.
Yeah. I think there's a difference in the information aspect. There is perfect information, but the issue is like how much information is being revealed across the boundary, which is of prime concern. I fail to understand whether your question was that information is, the interests are always aligned, is the issue there, or the fact is perfect information is not available even locally?
The way you're calculating it assumes that, in point of fact,
Mike?
Apologies. Okay, the way you're calculating it, in effect, it embeds the assumption that payoffs are symmetrical. And for that to be operationally realistic, in some ways they have to be, that's the way the providers have to perceive it as well.
Okay, so you're saying you're coming into the negotiation as equal partners. I think that can certainly change based on
maybe that's where I would diverge, because I would say in most situations that wouldn't be the case.
So, okay, I'll talk to you after the talk. There is a simple.
Randy Bush, IIJ. I'm that strange minority here. I come from an ISP. And I heard the presentation. I cheated. I also read the paper. And my perception, Tom, is that whether we come as equals or not, what matters is in this negotiation, I don't over-disclose and I don't lose. I may not gain as much, but I don't lose. And the truth is that as an operator, and an operator does peering, that's all I'm interested in. That meets my needs. I don't perceive myself as winning by you losing. And I don't, I'm here trying to make a better network, and I don't think the operators with whom I peer are bad actors. I like the fact that this doesn't encourage bad acting, and that it doesn't introduce a lot of complexity. And yet, I think a difficult problem, I smell that you're actually doing something useful, and thank you.
That's good. Thank you.